So welcome everybody. Our speaker today is Chunyin. He will tell us about homology and homotopy properties of scale-free networks. So we're all very excited. So please take it away.
Sure. Well, thank you for the introduction and thank you very much for your kind invitation. Today I'll talk about scale-free graphs and yes. So you may have seen a previous version on AATRN, but this time we have some new results on the homotopy properties as well. And it's my understanding that a lot of neuroscience people come to this seminar. So I also have a network seminar exclusive on some speculation on like what kind of relationship we could make with neuroscience. Okay, so what are scale-free graphs? So what you're looking at is a visualization of the internet back in the early 2000s. Each node is a web page and each edge is a hyperlink. And so topologically speaking, this is just a graph, okay? And it's homotopy equivalent to a circle, to a book of the circles, so it's not that interesting. But if you look at this like picture, and squint your eyes, you can kind of see there are probably some more structures to it. Like there seems to be a dense core, and it may even seem like a three-dimensional ball, okay, or four-dimensional, we don't know, okay, but it seems like there's a blob, and then there are some flares around it. Okay. So as topologists, we really want to have a more interesting topological description of these objects. Okay, so we want to study the topological properties. Okay. On the other hand, we have to keep in mind that like the internet is always evolving. Okay, so after I've given this talk, when this talk is uploaded to YouTube, the internet will be ever slightly changed. Okay, probably we do not want our description of the internet to vary too much when we have all these random fluctuations. So we should take into account like whatever randomness that's baked in the process of creating these systems. And all these point towards the study of random topology. So our object that we're studying is random, and we want to study the resultant topological properties of these things. Okay. So what I'm going to do is that I'll give a very brief overview of some very classical results in random topology. Then I will define a special class of scale-free graphs more precisely, namely preferential attachment graphs. Okay, so we'll be looking at more than just pictures. And then I'll share with you my recent result on the homological and homotopy properties of these objects. Any questions so far? Okay. So if you have any questions, I'm very bad at monitoring the chat, so feel free to unmute yourself at any point in this talk, and you don't have to wait until the end to ask questions.
I will also monitor the chat, but I think it's great if people just ask as well.
Yeah, great. Okay. Okay. Why random topology? So in TDA, the standard pipeline is that we start with a bunch of points, and then we build simplicial complexes, which is homotopy equivalent to your union of balls, and then we compute persistence diagrams, and then we say, these points are far away from diagonal, they're important, so on and so forth. Okay, all these standard pipelines. Underlying this standard pipeline is a philosophy that size is signal. Okay, you want to look at these big things and say, these is the important things. But that's not always true because like sometimes small things do matter. Like everyone should be able to tell that, okay, this is one, okay, my cursor is very slow somehow. This is one big square and this is one small square. And like we have no difficulty telling that this small square is actually there. But if we plot the standard persistence diagram, this small square will give you a point that's very near the diagonal. And if you don't look at the picture, you don't look at the picture. And if you just look at the persistence diagram, you'll be very tempted to say that this point is just noise and forget about it. So size isn't really everything. Okay? And as a probabilist, one thing that we can consider other than size is the element of surprise. What does that mean? We see that there is one square because this is a surprising phenomenon. If you sprinkle salt on a table, they probably do not line up on the rim of a square and refuse to fill in the center. Okay, but somehow these points do. Okay, so these points behave very differently from the behavior of random points, and that's why we think something is interesting is happening, and then we construct this topological idea that this is a square. Okay, so in short, signal is what is not random. And if you're familiar with statistics, this is just a very fancy way of saying we should compute the p-value, because p-value is saying how surprising your phenomenon is. But in order to actually apply this this philosophy into practice, we actually have to know what actually is random. Okay? We have to understand the behavior of random things, otherwise we can't distinguish what's random and what's not random. And that's why we need to study random topology. And so I will briefly discuss some very classical results on some very commonly seen random complexes. There are a lot more results since like around 10-ish years ago, but these are the most classical results, and I just want to give people a flavor of how random topology feels like. So I'll start with the Erdős-Renyi graph, which is a very classical object, random object. And the way to build these graphs is that you start with a bunch of points. Okay, these are deterministic. And then for every pair of points, you flip a coin and decide whether there is an edge between them. And all the coin flips are independent and identically distributed. And so let's say it's head, and you add an edge. Okay? And then you can move to another pair of another pair of points. You flip an edge, you flip a coin, and there's now a tail, and so you don't add an edge. And you do this for every pair of points, and you get something like this. Okay? So this is how you build an Erdős-Renyi graph. And there are a lot of classical results about these Erdős-Renyi graphs. This result by Erdős and Renyi, dating to 1960, says that there is critical threshold at which the graph becomes connected with high probability. And this threshold is log n over n. Now I'll write 1 over n here because I'll be foregoing log terms, because subsequently we'll see more pictures like this and the log terms will make things very complicated. So if your connection probability is low, you very likely get many different components. But once you pass through this critical threshold, your graph will be connected with high probability. This is a very old result that predates most of the TDA that we know. But as topologists, we don't have to just constrain ourselves to graphs. We can consider simplicial complexes. And the simplest way to cook up a simplicial complex out of a graph is to construct the clique complex. Okay? So we'll fill in all the triangles and tetrahedra and so on and so forth. Okay. And then you can consider the higher homological properties and ask, how does it behave? And if you run a simulation, this is what you're going to see. So the deep blue curve here is an illustration of the classical result that I've just mentioned. As your connection probability increases, your number of components will decrease, and after a certain threshold, you'll be connected. But that's not the end of the story, because if you look at the first Betti number, as the zeroth Betti number drops to 1, your first Betti number starts to rise. And it peaks somewhere and then it falls again. But as it falls, the second Betti number starts to pick up, and it peaks and it falls, and so on and so forth. Okay. So beyond the zero-dimensional behavior, we see interesting topological behavior as you keep on increasing the connection probability. And so this is really interesting. And there are theorems that describe what's happening. So the classical result says that there's this critical threshold, log n over n. But if you go beyond that, the first Betti number will start to dominate, in the sense that it will become large, and all other Betti number will be 0 with high probability. And the first Betti number will dominate for a while until you reach another critical threshold, and then the second Betti number will start to dominate, and so on and so forth. And the intuition is that as your connection probability increases, your holes start to get filled, and so the Betti number vanishes. But it has to build up at some point because the holes cannot form if your connection probability is too low. So this is the main intuition of why there are different regimes where different Betti numbers dominate. Okay. So this is a classical result for the Erdős-Renyi clique complex. And another class of complex that we use a lot, actually arguably more, in TDA is the Ribson-Chick complex, which I collectively call the geometric complexes. And the random version goes as follows. You start with sprinkling salt on table. The formal way of saying is to consider a Poisson point process. And then you connect points which are nearby, and then you do your usual Ribs complex and Chick complex thing. And then you get, oh, this is a graph, but then you add the triangles in tetrahedra, you get the Ribson-Chick complex. And since the points are random, and then you apply a deterministic process to get the simplicial complexes, these things are again random. And you can ask what the Betti numbers are for these complexes. And it turns out that it depends on two things. So first, it depends on the number of points. The more points you have, the more complicated behavior you could have. Very reasonable. And it also depends on the connection radius through this quantity omega. So omega is the number of points times the connection radius raised to the dimension of the space.
So the connection radius is the threshold at which you draw or don't draw the edge?
Yes. So you connect all. You have a simplex if all points are pairwise. The distance between all points are less than this radius. Okay. Maybe up to a factor of 2. So the expected Betti number depends on this quantity omega, which is the number of points times radius raised to the dimension, which basically counts the number of points within the radius R ball. And the idea is that if you don't have nearby points, you can't have simplicities, and hence you can't have Betti numbers. And if you have many, then something interesting happens. And turns out that again, you have these dense regime, sparse regime, and very sparse regime. In a dense regime, where you expect many points in your vicinity, your Betti number will decay exponentially. So basically, you're having so many connections that you're approximating the underlying space, and hence your Betti number will be small. You will be small. But if you have very few points nearby, now it depends on how few points there are. Okay? So if you have very, very few points, you can't really do anything. And so the expected Betti number tends to 0. But if you're few but not too few, you could have like some kind of spheres, or well, mostly spheres basically, forming in your tiny balls. And in this regime, you will have very large Betti numbers, in the sense that the expected Betti number will tend to infinity. And if you're interested in the precise asymptotics, this is the precise asymptotics. So again, we see the same phenomenon, that the Betti number is very small, and then it rises, and then it falls again. So so these are the behavior of these random objects, and I hope I've given you some ideas of how like results in random topology look like. Okay. So any questions up to this point?
Quick one. So the Betti numbers before were not for the RIPS, were for the Czech complex. Is that what Czech
Yes.
means, or something else? Okay.
Yes, it's for the Czech complex. There are analogous formulae for the RIPS complex. It's just that it's a very dense slide, and we don't want to overload the slides with too much information. It's a slightly different formula, but looks kind of similar. So I think this paper has both results for RIPS and Czech. This result is true for both RIPS and Czech though. Good question. Thank you. Okay. If there are no other questions, we'll talk about preferential attachment. So for both examples we've seen and for a lot of results in the literature, people have looked at very homogeneous random objects. So for the Ernest-Rene graph, all your edges are independent, and for the random rips and random check complexes, like you assume the points are fairly uniform. But a lot of objects in the world are not that uniform. This is definitely not uniform. Right? If I put my YouTube video out there, it's probably not going to make a big impact. If Elon Musk make a tweet, that probably has a much bigger impact than mine. So the world is inhomogeneous, and so if we want to approximate the world in more accurately, maybe we want to have some models that are not that uniform, not that homogeneous. Okay? And of course, I'm not the first person to think about this, and there have been other people who were trying to come up with models that capture the inhomogeneity in the world. In particular, Albert and Barabasi proposed this preferential attachment graph model back in 1999. In order to describe the model, I'll content myself with a much simpler picture than this. Okay? So the model goes like this. You start with a small graph, okay, and you add new people to the graph, and these people will, well, by people I mean nodes. These people will more likely attach to already popular people. Popular in the sense that the degree is large. And the formal way of saying this is that the probability of attachment is proportional to the degree of the existing node. And I'll add this tuning parameter delta so that I have a family of models as opposed to just one model. Then I have some flexibility of choosing what this parameter is when I see an actual graph out there in the real world. Okay, so this is how we update the graph at every step. So we've attached this person to an existing node. We update the graph. We update the degree sequence, and then we add more people to the graph. Now, since everyone wants to make friends with the already popular people will become ever more popular. This is known as the rich get richer effect. Okay. And so at this point, any question about the model setup? Okay, now, so we actually know a lot about these graphs. After all, they've been around for 20-ish years. For example, we know the degree distribution. This is one of the earliest results we know about these graphs. In fact, these graphs were proposed to try to explain why we have these power law distribution in the degree. So we know a lot about the degree distribution. They obey a power law. You can look at the power and then try to say something interesting about it. We can also count triangles in these graphs, in the sense that we know the asymptotics of the number of triangles in these graphs. There are not that many, but we can count them somewhat precisely. Since the clustering coefficient is closely related to triangle count, basically triangle counts, we have good asymptotics of these clustering coefficients as well. And we do not have to stop at triangles. We can actually count arbitrary subgraphs. We can count tetrahedra, we can count pentagons, any small graphs. We can write down the asymptotics of the expected number of such graphs. Okay, so we know quite a lot about these objects. But since we know a lot, but since we're topologists, we would like to know the topological properties, which is much less explored. And the first order of business is to construct some kind of topological objects that's more complicated than the graph, and the simplest way to do this is to construct a clique complex. And so the object we're going to study is the clique complex of the preferential attachment graph. And we'll try to look at the homology and the homotopy properties. Okay. This is John. Yeah.
Sorry, I interrupt you for a second, but some really weird echo started in the last slide. I don't know if you have background noise or maybe you can move closer.
Okay. Is it still? Can you still hear the echo? 1, 2, 3, 4.
I don't know if it's an echo. It's like a wave or something hitting something.
Okay. It may be my air purifier. Let me try to close it. It could also be the rain out there.
Yeah,
I'm
if
not
it's the
hearing
rain, there's
anything strange.
Sorry?
I'm not hearing anything strange.
Oh, I asked at least one other person so to check before. So, oh, it stopped.
Has it stopped?
It stopped.
Okay, it's the air purifier.
Okay.
Okay, well, thank you for letting me know. Okay. And that was a good point to pause. Okay. So, I'm going to talk about the topology of these objects. This is joint work with my PhD advisor, Professor Sam Wonitzki, my co-advisor, Professor Yu, and my then undergrad mentee, Evan and Rungi, who are now both grad students. Okay. The beauty of Betti numbers is that you can just compute it, and so let's compute it and see what happens. Okay. So if you run a bunch of simulation, this is what you're going to see. The x-axis is the number of nodes. You can interpret it as time. So as time goes on, you have more and more nodes. The y-axis is the second Betti number. Each curve you're seeing is one random instant of a preferential attachment graph. So you build a preferential attachment graph with like I think 100,000 nodes, and you look at the evolution of Betti numbers, and then you throw this graph away, generate another one, you get another curve, and then you do it many times, you get many curves. Okay. There are a number of observations to be made about these graphs. First of all, these curves are all increasing, which is kind of surprising because all the examples we were looking at, they tend to increase peak and fall. So for these graphs, the Betti number just generally increases. Another observation is that the growth is concave. This is not too surprising because if you look at the asymptotics of the triangle counts and other subgraph counts, they're all sublinear. So, and since you need these higher order simplices to construct these cycles, like we don't expect these Betti numbers to grow too quickly. And the third observation is that this curve can be considered an outlier because the Betti number for this graph simply grows much faster than others. Okay. And please note that I use the same model parameters for all these curves. Okay, so they should have the same they should have similar behavior. The presence of outliers is not too surprising in the context of preferential attachment because, well, as we have seen, these graphs are known to produce these like so-called hub nodes, which are very well connected. And from the perspective of the degree distribution, they can be seen as outliers. And in this case, we also see that this is like an outlier. The mechanism in which these outliers like occur is different, but I'm simply making the point that like we generally expect some form of outliers when we talk about preferential attachment. Okay, so these are the empirical observations, and we can actually prove theorems to describe these phenomena. And this is a theorem. So we can prove that with hyperability, the second Betti number, will be bounded between constant multiples of the number of nodes raised to an ugly power. And this ugly power takes the form of 1 minus something, so it's a sublinear power. And of course, this something depends on the strength of preferential attachment. The stronger the preferential attachment, the larger the exponent. And that's why we see this concave growth behavior. Now this 1 minus something begs the question of, okay, when this exponent is negative, does it converge to 0? I don't have a formal proof, but the answer should be no. We can only show that the second Betti number is bounded from above with high probability. It probably doesn't converge to 0 because convergence to 0 requires the presence of boundary terms to kill off the cycles. And when this negative, you tend not to have many of these boundary things. So I don't think it converges to 0, but I don't have a formal proof. And there's nothing special about the dimension 2. If you replace the dimension with if you replace the number 4 with 2 times the dimension, you get exactly the correct result for higher dimensions. Now pause for a few seconds for folks to read this very verbose slide. Any question? Okay. Now, this is a very quantitative statement with a lot of symbols floating around. This is a more pictorial way of depicting this information. Okay. So one can show that for all choices of parameters, the first Betti number will exhibit unbounded growth with high probability. This is a pretty straightforward Morse inequality argument. However, if you keep on increasing the strength of preferential attachment, at some point you'll reach a critical threshold beyond which your second Betti number will start to exhibit unbounded growth. And this is simply because the second Betti number is number of nodes raised to some power, and when this power becomes positive, it exhibits unbounded growth. Now, if you further increase the strength of preferential attachment, your third Betti number will also start to exhibit unbounded growth, and so on and so forth. So, like the previous random topological objects we've seen, there are different regimes where the topology and there are critical thresholds between these regimes, and across which the topological behavior changes quite drastically. Okay, and I'll briefly sketch the proof. It will be a mostly pictorial proof. The main idea of this statement is that you can approximate the Betti number with the number of spheres in these objects. And if you count the number of spheres, you get the right asymptotics. So this is a sphere, but these spheres may or may not be intersecting. So this is 2 spheres. These are 2 spheres that are intersecting. So you have they share one equator, but you have 3 poles to choose from. So what I just said was technically not correct. You should not be counting spheres. You should be counting hemispheres, or in this case, filled squares, because the Betti number grows linearly with the number of poles you can choose from, and the number of filled squares also grows linearly with the number of poles you can choose from. And if you count the number of filled squares, you basically get the correct count. And the difficulty is, of course, to find ways to precisely say that Betti numbers is approximately the number of such squares. Okay, so I've kind of hand-wavily proven this result. Now, at the beginning of the talk, I promised that I'll talk about homotopy connectivity. And now I've shown you that the Betti number is like this ugly thing, And since homotopy is generally more complicated, and if the Betty number is already complicated, you shouldn't expect anything simple and nice, okay? At least for mortals like me. However, if you have the wisdom to pass things to infinity, there may be some hope, as I was told in a private conversation. After all, the infinite sphere is contractible, even though individual spheres have very ugly homotopy groups. And in this particular case, passing things to infinity helping you may not be that magical. And I'll show you an example where the Betty number keeps on increasing in a finite setup, but in the infinite setup, it vanishes completely. So you start with an empty square. It's a topological square. Next step, you fill it up, but you add 2 more squares. Now the Betty number increases. Next step, you fill these 2 up, and you add 3 empty squares. So every single time your Betty number is increasing because you're adding more and more small squares. But as you keep on going, the infinite thing, which is the union of all these things, is just like this filled staircase, and so there's no topology whatsoever. So it's not a pathological phenomenon. It's not a magical phenomenon. If you like to think in terms of persistent homology, the idea is simply that you have a persistence diagram where you have infinitely many points, but each point has a finite death time. So everything dies, and so when you look at the infinite thing, nothing survives, and so it doesn't have any non-trivial behavior. So the hope is that if the growth in Betty number, indeed topological behavior, is driven by these small spheres, if we can fill up all of them in finite time, not necessarily once and for all, but if every one of them dies at some point, then the infinite thing may be nice. Now this is again a wishful thinking because this is just the things that drive the Betty number. Something more complicated may be happening for the homotopy setup. But it turns out that there are nice theorems that allows you to prove whether something is homotopy connected, okay? Due to Barmark. So Barmark has a more elaborate statement for simplicial complexes, but I'll just state the version for clique complexes. So it turns out that if every small collection of nodes has common neighbors, then you can show that the complex is homotopy connected up to some dimension. And the game is that for every such thing, you wait long enough. Now, in the preferential attachment setup, you keep on adding nodes, and they may or may not make friends with these nodes. You just keep on waiting until one node makes friends with all of them. Then you have basically combed this hole, and so this kills off the hole. And so the question is can you do it for every single small collection of nodes? And if you do the computation, it turns out you can, up to some dimension. So you can prove that almost surely the infinite clique complex is homotopy connected up to some dimension. And of course, the dimension depends on your strength of preferential attachment. And this threshold, again, is tight in the sense that if your preferential attachment is just slightly smaller, your Betty number will be infinite. Now, this is again a very quantitative statement, but again, we can draw pictures. So from left to right, the strength of preferential attachment increases like before. I just phrase things in terms of x because it's simpler. So if your strength of preferential attachment is weak, your first Betty number will be infinite. And then you have finite Betty number for higher dimensions. But as you keep on increasing after this critical threshold, your infinite complex will become simply connected. So one homotopy connected is just simply connected. But you can show that the second Betty number will be infinite. And then you keep on increasing the strength of preferential attachment, and then the second homotopy group will also vanish. and so on and so forth. And the critical threshold, 2/3, 4/5, and 6/7 is exactly the same as before. So 2/3, 4/5, and 6/7. Okay. I'll let people stare at this picture for a few more seconds. Okay.
Is
so
there like an
yes.
is there an obvious reason as to why the thresholds are the same for the homotopy and the homology?
I'm not sure if it's obvious, but the argument is kind of similar. Well, are they similar? Well, first, the Betti number argument is definitely similar because so to show that the Betti number is infinite, you just show that, well, if you take the limit, you're doing the right thing. Okay? That takes some justification because you have some sort of category theory thing going on. But for Homo to be connected, okay, I proved this a while ago and have to recall. I think the computation is natural, and my impression is that like the thresholds just happen to be correct. At least that's my impression when I was doing the computation. And I was actually very scared when I was doing the proof because I was afraid that there may be gaps, and then I have to like fill in the gaps. It turns out that there's no gaps. So I do not have better insight why it just happened to follow through. I mean, after all, you're also kind of counting spheres because you're looking for things that I guess a higher level answer will be so most of these holes are driven by small objects because for random simplicial complexes, generally complicated objects do not arise frequently. So the holes or Betti numbers, they're generally coming from small objects. And the smallest thing you can have is spheres. And so basically spheres, and when you try to add cones of these small things, the smallest example is also a sphere. So I think like the something about like the minimality of the sphere may be common to like both arguments. Yeah, but thank you for the question. Okay, any other questions? Okay, so in short, the strength of we've shown that if the strength of preferential attachment is strong enough, then the Betti number of the finite object grows sublinearly with high probability, but the infinite object will be homotopy connected up to a certain dimension almost surely. Okay, we're almost at time, and I've prepared some speculation on neuroscience because I assume that some of our audience members would be interested. And I do not have concrete math result in this section. It's mostly me trying to have a conversation with the neuroscience community. And so I treat this as an opportunity for me to ask some questions into the void. Okay. For context, I'm now at the Stanford School of Medicine trying to help people analyze whole brain functional MRI. And the goal is to try to understand depression, ADHD, and other psychiatric conditions. It's my understanding that people in this community, they're usually neuron level people. So I know very little about neuron level things. And so here are my questions for neuron level neuroscientists. Okay, so we're looking at neurons in the brain. And obviously, it is not a completely random graph. Hopefully, something more sophisticated is happening in our brain or in the brains of mice. And as a probabilist, like it's an interesting question for me, like how one should model it. Presumably somebody may have come up with something, but I'm just not very familiar with the literature. So I would speculate that local connections are more likely. And at the same time, I'm not very sure whether preferential attachment is a good model. At least for sure, neurons do not quote unquote arrive one by one. There's some literature that says there's some kind of like power law behavior happening. I'm not very aware of any like mechanism that may be driving that. So that's one interesting question for me, and I'm curious what other thoughts people have. And personally, I think like this is my speculation of what a nice model might look like. So I will proceed with A, whether the neurons distribution is reasonably spatially uniform. If that's the case, that may make a case for like modeling it like a Poisson process. And then for the nerve fibers, the question is, so do they depend on distance? Do they only depend on distance? Now, if it depends only on distance, that makes a case for like a geometric graph. And so these are some like very high level, unrefined questions that I have when I approach the neuron level neuroscience community. And if anyone have any thoughts, I'd really appreciate knowing your thoughts. Okay, so these are all the slides I prepared for you guys. If you're interested in the results for preferential attachment, I think this paper is the homology paper. This is the homotopy paper. And I've also given a talk on how to find small holes. And you can scan this QR code and you get that video. I'm Chunyin at Stanford. Thank you very much for your invitation and your time. And I'm happy to take questions.
So before answering any questions, maybe we can all unmute ourselves and clap in real life. So thank you, Chunyin, for the talk. I really enjoyed it. There's already one question in the chat, so maybe we address that one first. Okay. You did answer it in the beginning, but I think maybe more detail would be useful. Do we know anything about the degree distributions of these networks?
By these networks, I think you meant like preferential attachment graph as opposed to neurons.
This is
No,
psi,
I
right?
meant the neurons, sorry.
Oh, you meant the neurons.
Yeah.
To be very honest, I haven't looked at the literature. I think there are probably better people than me in this audience to answer this question. But I vaguely remember seeing something like there are some kind of power law distribution.
So some networks have some power law distribution, some other ones don't. And I think it depends if you're, so these networks often have a notion of direction. And depends if you look at the incoming degree or the outcoming degree. And I think one cannot say that it's always following a power law, but they're often very long-tailed. This much we know. But preferential attachment follow a power law, yeah?
Yes, preferential attachment do follow power law, but arguably there are other mechanisms that drive a power law behavior, and probably the power law cannot hold to universally simply because these things have biological constraints, and like you cannot have like, you know, the degree cannot be too large. So something more nuanced is probably happening.
So I actually like looked at the distributions of the degrees of some species on the neural level, like worm, fly, part of rat or whatnot. And in, I don't remember now if it's incoming or outgoing, the reason why there's no power law, they kind of drop at the low degrees. So they go like this and they drop at the low degrees, because I think it's maybe not so likely to have some very sparsely connected neurons. So the shape
so you're saying that we do not, so the degree cannot be too low, right?
Yeah,
okay.
That's my guess. Do other people have other questions?
I have a question. So you're taking the preferential attachment graphs and then you're looking at the clique complex, right? Have you looked at other types of complexes, such as the neighborhood complex? Because I know Kale has some results on this for neighborhood complexes of Rosrenes, I think. Have you looked at those?
I'm not familiar with the neighborhood complex. So okay, the short answer is no. I've briefly thought about the path homology, so that I don't have to pass through clique complex. But path homology is kind of difficult to do computation and simulation. So it's probably a lot of work. But I do believe similar arguments should follow through, because the main idea is that the growth in Betti numbers should be driven by the smallest object intersecting in complicated ways. So then the question is, what are the small objects in the other setup? Yeah, so this is a long answer to a non-question, to other question that you didn't ask. But to your question, the short answer is no.
Fair enough. Nice.
And another thought is that it is difficult. So all these Betti numbers are driven by small objects. Okay, I do not remember how one constructed neighborhood complex, but these things have very small diameters. For the infinite complex, the diameter is, I think, log n. No, for the infinite thing, the diameter is 2. And if for very big finite thing, the diameter is log n being number of nodes. So even if you look at this like two-step Rips complex, you get something very boring very quickly. You definitely get something boring for the infinite version. For the finite version, you may still get something, but log n is very difficult to simulate. You need very, very big graph to get something that's possibly not trivial. Yeah.
Cool. Yeah, I mean, the neighborhood complex is generally defined as the maximal, every simplex is any subset of vertices with a common neighbor. Or equivalently, you can think of it as the maximal simplices are the neighborhoods of the vertices. But I think you have a problem here is that trying to compute anything on these, in this case, would probably be difficult because these tend to have very high dimension because the neighborhoods in these things are going to be fairly large.
Yes, because most of these nodes, they're probably connected to some like central hub nodes, and so you probably have many very high dimensional things, and arguably these things will not, and very few of them will contribute to your homology, because probably like once you have the cycles, it becomes a boundary very quickly in some sense.
Cool.
Thanks for the question.
Do we have other questions from the audience, maybe? I have a quick question in case someone wants to think about their question. So you said you looked a little bit path homology and these things. So then
I thought a little bit. I didn't try to compute anything.
That's fine. How are you thinking about preferential attachment then in a directed sense? Because this involves direction.
So there are known results for directed preferential attachment graphs. The in and out degrees still have some kind of like basically power law behavior. The fancy word is regular variation. The topology, I don't think people have looked at the topology. With the directed graph, if you just want to stick to clique complexes, you already have to make choices of which clique which version of the clique complex you want to work with. So there are some like very foundational things that some basic bookkeeping that one has to deal with before you start to do any computation.
So in this model, when you add a vertex, you add both in edges and out edges?
In this model, it's undirected. So
no, I mean
edges
in
are
the model you were just talking about.
So in the model I was referring to, from what I remember, every time you you somehow randomly select whether you want to add a node or you want to add an edge. And if you want to add an edge, you have to direct it somehow. That's what I remember. I'm not entirely sure whether that's correct. But so it's and once you've defined this model, you can still like look at the degree distribution for in and out degree. And and there are techniques from regular variation people that to deal with these things, but they have mostly looked at the degree as opposed to Betty numbers. Yeah.
Thanks.
Are there maybe any other questions from somebody else? No. In that case, I mean, we can ask some questions that are not recorded.
There's a question in the chat.
There's a question in the chat. Oh, yes, right. Did you think of model this with hypergraphs?
The short answer is no. And I'm blanking on whether I've seen preferential attachment hypergraphs. And my guess would be somebody should have tried it, but I'm not familiar with what they have done. And yeah, I don't have a better answer than that. But I would assume that if you Google preferential attachment hypergraphs, you get a bunch of results.
Okay, there are no more questions in the chat anymore. Does anybody have another question? Because we can ask questions that are not recorded, but I'll give you a last chance. No? Okay, then let's thank Chunyin once more time before we stop recording. You can unmute yourself and clap.
Yeah, thank you so much for coming.
Thank you for your talk.